Okay, hello, grade 11. So that gets us to Newton's law of universal gravitation. Now, this tells us that the force of attraction between any two masses in the universe is called the force of gravitation. Gravitational force is directly proportional to the product of the masses and inversely proportional to the square of the distance between the object. So we can literally express this symbolically by saying the force is directly proportional to the product of the masses and the force is indirectly proportional to the square of the distance between them. Now some books do, instead of having d squared at the bottom there, use r squared. Do not get confused with little r squared and say no, but it's radius. It's not. It's got nothing to do with radius. So then we can go and we can express it in saying if we have mass 1 and mass 2, they will be expressing equal but opposite forces to each other, and this will always be a force of attraction, and they are distance r apart. So we can say that the force of attraction between them is equal to capital G times the product of the masses over r squared, where this capital G is what we call the universal gravitational constant. Okay, so if we have object 1, the Earth, and we have object 2, then we can say that the Earth has a radius of r. Okay, and this would be if the object is situated on the surface of the Earth. Okay, if we then go and we have move the object a little bit further away, let's say to 2 times the radius of the Earth and to 3 times the radius of the Earth, then we can see what happens to the distance and the weight. So every single time, because we have the object on Earth, we know that the weight will simply be 1 unit. But if we're on 2 times the distance, all of a sudden we get a quarter of the weight. And this is because of the fact that the distance and the force are indirectly proportional to each other, but it's also an indirect root rule or square rule there because it's distance squared. If we have 3 times as far, we see that it's only 1/9 of the weight. Okay, and it's very important to remember this for when we do our descriptive problems. Okay, so Newton's law of universal gravitation tells us that every particle in the universe exerts a force of gravitational attraction on every other particle. The force between the two particles is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Mathematically, we express it as F is equal to G times M1 times M2 over D squared, where capital G is the universal gravitational constant, and it has a value of 6.67 times 10 to the power of negative 11 Newton per meter per meter per kilogram per kilogram. Now it's very, very important to understand this, guys. This means that everything that's got mass is attracted to everything else that's got mass. You're attracted to the Earth's attracted to you, you're attracted to the moon's attracted to you, the moon is attracted to the Earth, and so on and so on and so on. So it creates this underlying force of attraction where everything is pulled to everything that kind of keeps everything where it's supposed to be. Okay, so if we then go and we take a look at the following situation. So we have 2 little metal balls and they are suspended by a string, and then we have 2 larger metal balls. Now, the value of G was determined by Lord Cavendish using the following apparatus. In the experiment, the force of attraction between the spheres was measured and G could thus be calculated. And now this is incredibly impressive because this was done many, many years ago. And literally when he hung the 2 little balls in between the others, they slowly but surely attracted to each other. Okay. Now, we can also then go and we can say, now for the terminology, free fall, what we need to know, an unimpeded fall where only gravitational force acts in on the object, and depending on where we're falling, it can be up or down. Terminal velocity during free fall, the velocity an object has when the upwards air resistance is equal to the Earth's downwards acting forces. So in other words, as soon as the object starts moving at a constant velocity, we get the terminal velocity. Gravitational acceleration is the acceleration of an object in Earth's gravitational field. Okay. So the value of small g varies over the Earth's surface. At the equator it is less, and at the poles it is more. So we usually just use 9.8 meters per second. Now, the value of g is independent of the mass of an object in the Earth's gravitational field. This can be shown mathematically as follows. So if we drop an object, we can say, right, the force between the object and the Earth is given by the following. So we use the universal gravitational law. So we've dropped that tennis ball and it fell, and then we can express it as saying the force of attraction is equal to the universal constant times big M, the mass of the Earth, times small m, the mass of the object, divided by r squared, the distance between them. Okay. Now, according to Newton's second law, we know that the net force is equal to the mass times the acceleration. So in the term of force due to gravity, it would be the mass times the gravitational acceleration. We substitute that in, and we find that the mass times the gravitational acceleration is equal to the universal constant times the mass of the Earth times the mass of the object divided by the distance between them squared. The mass of the object cancels out, and we get to our equation to calculate the gravitational acceleration of our object on a specific planet. Now, the acceleration g is thus dependent upon mass and radius, and not the mass of the object, but the mass and the radius of the planet it is on. The gravity on any planet is thus calculated this way. Now, gravity on other planets. Now, the mass and the radius of the respective planets determine the gravity. And if we take a look at, for instance, the following, where we use the gravity on Earth as 1, and we compare the other planets in our solar system, we can see that Mercury has about 0.4 the gravity of Earth. Venus has about 0.9, Mars also 0.4, and then we get to the bigger planets like Jupiter, which is off the scale. Okay, so the size of the planet, in other words, the amount of stuff the planet is made of, compared to the actual radius of the planet, will determine the actual gravitational acceleration on that specific planet. It's one of the reasons why you can see when people are on the moon and they jump, it looks like they're floating through the air. It's because of the incredibly low force due to gravity. Now, mass in kilograms is the amount of matter contained by a particular object. It always has the same value, irrespective of the position in the universe. And it can also be described as follows. A measure of how much an object resists a change in its state of rest or uniform velocity. This is known as the inertial mass. So the amount of stuff something is made of. Weight, however, is a force. Now, if we take a look then, and we go and we take a look at the chemical balance, measures mass of an object. So here we have it, okay? And if we have a little mass pieces and objects placed in one pan, and the mass pieces placed in another pan, this determines the mass of an object, okay? Weight, on the other hand, the weight of an object is a measure of the gravitational force of attraction exerted by the Earth on an object near to the Earth's surface. That's not just the Earth, it depends on the planet you're on. So the force due to gravity is equal to the mass times the gravitational acceleration. Here, the force due to gravity is the weight, small m is the mass, and small g is the acceleration, or the gravitational acceleration. On Earth, it's 9.8 meters per second per second. Now, since the radius is different, g is also different from point to point on the surface of the Earth. Okay, what's weightlessness then? Now, the sensation of weightlessness is what we experience when our weight appears to be zero, even when in a gravitational field. This happens when we're in free fall. So astronauts experience this sensation while orbiting the Earth in their spacecraft. They are experiencing the same acceleration as the spacecraft and the floor exerts no force on them, thus the feeling of weightlessness. So even though something appears to be weightless, it's still experiencing a force due to gravity. It's just the person in the space shuttle and the space shuttle are accelerating towards the Earth at the same rate, and that gives that perception of weightlessness.